Okay, welcome back. So what we'll talk about today is polynomials in several variables. So all along we have only talked about polynomials with a single variable x, but of course that's you can generalize that. Let's do two variables. Let's call the variables x and y. So here is an example of a polynomial in two variables, right. So let us start with an example. Okay, so I wrote down a long example. So 1 plus x plus y plus 2x squared minus 3xy plus 3y squared plus 7y cubed. So well, what is this? It's so how do you define a polynomial in two variables, for instance? Well, it's got terms of the form some power of x multiplied by some power of y. So those are terms which are referred to as monomials. So what's a monomial? A monomial is just a term of the form x power I, where I is some non-negative integer, times y power j, where j is again a non-negative integer. So I and j are 0, 1, 2, 3, 4 and so on. So that is of course what is called a monomial, and a polynomial of degree in two variables x and y is nothing but a linear combination of monomials, which means you take various monomials, you multiply them by some constants in front, you take finitely many monomials, multiply them by constants in front and add them up, right. That is what we have been calling linear combinations throughout. So an important notion here for a monomial is that of degree. So just like for polynomials in one variable, the power of x, the largest power of x which appears is called the degree of the full polynomial. If I take just a single monomial x squared, we say this monomial is of degree 2. Similarly, if you have two variables x and y, you say the degree is a sum of the two powers. So the degree of this monomial x power I, y power j is just I plus j, okay. So if you sort of look at these things here, the monomials which appear in this expression, I have 2 degree 1 monomials which appear, this is of degree 2, xy is of degree 2, y square is of degree 2, y cubed is of degree 3, okay. So you have monomials of varying degrees. Now here's an interesting counting problem. So I want to do the following. I want to count the number of monomials of degree d. Find find the number of monomials of degree d. Of course when I say this, I should also tell you how many variables I have, okay. So observe, this depends also on the number of variables. So let us just take examples. So here I only talked about polynomials of degree 2, but of course it is easy to see what you do in general. If you had x, y, z, you would just say a monomial is something of the form x power I so here is what a monomial would look like if you had 3 variables. So let us do this for one variable. Suppose I only have, so when I say n variables, n is 1, so I only have a single variable x. I am going to do the following. I am going to write down the monomials of each degree. So if I have degree 1, there is only x power 1. If I have degree 2, I can only do x power 2. If I have degree 3, I can only do x power 3 and so on. Similarly, if I have degree 0, I can only do x power 0. So here it is very simple, there is only one monomial of each degree, okay, and so on. So for every degree there is exactly one monomial. Now let us do the same thing if n equals 2. Okay, so I have two variables x and y. Suppose I have n equals 2, I have two variables x and y. Let us do the same thing. Let us write down for each degree, let us write down all the monomials. And let us count the number of monomials. Okay, so again degree 0 is easy. I can only have a monomial x power 0, y power 0. Right, that is the only way in which the sum of these numbers can be a 0. So there is only one monomial of degree 0. Degree 1, I can either have x power 1 or I can have y power 1. So there are two possibilities. If I want degree 2, so I can either take x squared, which means the total degree is coming only from the x, or I can take x power 1, y power 1, or I can take y squared. So there are three possible monomials, each of which would have degree exactly 2. Okay, so this is now 3. Let's do the same thing. Degree 3 is x cubed, x squared y, x y squared, y cubed. So there are four monomials of degree 4 and so on, of degree 3 and so on. So again here it is pretty clear how this is going to go. If I have degree d, then here are the monomials, x power d. So I subtract 1 power of x, increase 1 power of y, so on, keep doing this till I finally land up with y power d, and there are exactly d plus 1 such monomials. Okay, so we have managed to figure the answer out in both these cases. If you only have one variable, there is exactly one monomial of each degree. If I have two variables, there are d plus 1 monomials of degree d. Okay, so of course the next thing to do is to look at three variables. Suppose I have x, y and z, let us do the same thing. Let me write out the monomials and then we will count the number of monomials. So again degree 0 is easy, there is only one, x 0, y power 0. Okay, so here we have the following monomials. There is one of degree 0, there are 3 fellows of degree 1, there are 6 of them of degree 2. Now here we get to the interesting part. How does this go on? So of course it is going to be very difficult to figure out the general degree d case unless we have some more systematic way of approaching this problem. So let us do the following. So suppose I want to write out all monomials of degree 3 involving the variables x, y and z. Here is what we will do. Let us only write down the monomials which involve x and y, those which do not have z in them. Okay. Now that problem we have already solved. We know which are the monomials of degree 3 in only x and y. So those are these 4 fellows, x cubed, x squared y, x y squared and y cubed. Okay. So let us write those down. So it is x cubed, x squared y, xy squared and y cube. So those do not involve the z. Okay. Now let us do the following. Suppose we also want things which have let us see. So okay, great. So now we also want to know which are the ones which have a z in them, right. So these are the ones which do not have z. So we already have a count of 4 there, plus the ones which do involve a z. Now let us look at the ones which involve a z. What are they going to look like? Well, they are all going to have at least a z power 1, right. So they are going to, each of the polynomials here which are, so I am going to write them down here, they are all going to have at least a z. Okay. So let me pull out that power of z and then figure out what is left. Okay. So if I write out a monomial of degree 3 which has z power 1 in it, what is left must again be a polynomial in x, y and z, a monomial in x, y, z, but of one lower degree, because z power 1 already accounts for degree 1. What I am looking at is just the remaining degree. Okay. So what I do is I take each of these preceding polynomials and I multiply them by z, that is all I need to do. So I take each of them, so I have x squared times z, so I have written it like this, z x squared, z y squared, z multiplying z squared, z multiplying xy, z multiplying yz and z multiplying xz. Okay. So each of them has some z in it, so that z you pull out and what is left is just a degree 2 monomial, so something of one preceding degree, and that number we know there were exactly 6 of those. So we know the answer now, it must be 4 plus 6. Okay. Now this thing that we just did here, this basic idea, the procedure is very important. So So let us do the following, let us give this number a name, let us call the number of monomials of degree d in n variables, let us call it a of d comma n. Okay. So that is the number. So what we have just proved here, if you sort of look at the argument here, it says the following, if I want to say how many monomials there are of degree d using all the n variables, here is what I can do, I pick one of those variables, I take the last variable and I look at the monomials which do not involve the last variable, not containing the last variable. Okay, so these only involve the first n minus 1 variables. Now the monomials of degree d which involve the first which only involve n minus 1 variables is of course the number is just whatever we are calling a of d comma n minus 1. Okay, so that is those which do not contain the last variable plus the ones which do contain the last variable. Well, for that the idea was the following, you know that the last variable will surely appear to at least power 1, you pull out that last variable and you see what is left. So just what we did here, you pull out the z and what is left is again something in n variables which has one smaller degree. Okay. So plus number of monomials of degree in n variables but of one smaller degree, take every one of them and hit it by z where z is the name of the last variable. So this fellow here actually counts, this counts the number of monomials which involve the last variable, which contains the last variable. Right. So by taking care of these two disjoint cases, what you obtain is the total count. This is all possible monomials of degree d. These are ones which do not contain the last variable and that counts the number which contains the last variable. So this is now exactly what we kept calling it a recurrence relation when we talked about the Chebyshev and the Legendre polynomials. This is now a recurrence relation again, but it is a recurrence with 2 variables, so it is somewhat more complicated. So observe, so this is again a recurrence relation. Meaning it determines the value of a, d, n in terms of somewhat lower values, either n is smaller or d is smaller. Now firstly we should say this recurrence is valid for what values of d and n? D should be at least 1 and n should be at least 1. Right, the total degree is, so I am assuming that, so on the right hand side I have d minus 1, which means this is at least 0, and I also have n minus 1 occurring, so it is at least a 0. So now we have a recurrence relation which is valid for both d and n at least 1, and whenever you have a recurrence relation you need some initial conditions as well, meaning you need to know what happens when d is 0 or you need to know what happens when n is 0. Further we know the following things. The number of, so let me look at what is a0 of n, and let me also ask what is a d of 0. These would be our initial conditions. So a0n would be, let us read this, it is the number of monomials of degree 0 in n variables, right. So we have already done this, there is only one monomial of degree 0, which is x power 0, y power 0, z power 0, blah blah blah, every variable power 0. So there is only one fellow for all n degree 0. So that is easy. Now what about the next thing, a of d comma 0, okay. So d comma 0 is okay, so that is probably not something that we would want to do, because I mean we would have to define this. So let me just modify this. So let me say I want at least one variable, I do not quite know what it means to have 0 variables. So then this equation is only true if n is at least 2, right, because on the right hand side I have a n minus 1 occurring, so which means this should be at least a 1. So let me do this, what is a d1? This would be the number of monomials of degree d in a single variable, right, and that again we have done. There is, if we only have one variable x, then for each degree d there is exactly one monomial which is x power d. So this is also a 1 for all, so I should have said for all n at least 1 here, and this is for all, okay. So these are the initial conditions. Now this combinatorial problem here is best expressed in terms of a table. So what we should really do is write a table with various values of d and n. So let me just do this, d is on top, n is on the bottom. The degree can go from 0 so the degree goes from 0, 1, 2, 3 and so on. The number of variables goes from, it is at least 1 here, so the degree goes from 0, 1, 2, 3, the number of variables ranges from 1, 2, 3, 4, right. Now what we have said here is the following, a0n means if I put d is 0 and n to be anything, the value is 1. So what I am tabulating here are the values of adn, so this is the table of values of adn. So I am tabulating them. What it says, the first column contains all ones, Okay, so what this says is that the first column, so if you plug in d equal to 0 and take any value of n, it's all 1s, and this condition here says that if you plug in n equals 1 and then take any value of d, the values are again 1. So certainly the first row and the first column have all 1s in them, and now what the recurrence relation says is if n is at least 2, which means you are at least from the second row downwards, and if d is at least 1, so which means you are at least from this column here. So ADN for all these empty boxes is what the recurrence relation tells you. It says that if you want to compute the value of ADN in any box, if I want to know the value here for instance, what I need to do is to look at the one lower value of d. So the value here is the sum of the value in the box above it and in the box to the left of it. So all it's saying is that it's just the sum of the values in those two boxes. Okay, so by sort of doing this iteratively you can find the values in all the boxes. For instance, now I know if I want to find this box here, it's the sum of 1 and 1, so that's a 2. This box here would be the sum of 1 and 2. Okay, so what I have done now to fill the table is more or less use the property that the value in any box is the sum of the value in the box above it and in the box to the left of it. So here I have, you know, this row is 1 2 3 4 and so on, the next row is 1 3 6 10 and so on. So these are the things that we already had computed, and now observe that if you wanted to know for 4 variables the number of monomials of any given degree in 4 variables, that is given by this formula here, by this table 1 4 10 20 35 56. In 5 variables it is given by this and so on. Okay, so at the moment this might look like some strange numbers that we are generating, but hopefully it is not all that unfamiliar. So in order to sort of get a better perspective on this, one should sort of read this in the following way. So imagine there is a 1 1 1, so I read it diagonally, and so on. Just a 1. So if you sort of read this table in this diagonal fashion, then I hope these numbers are somewhat more familiar from other contexts. Okay, so we will again return to this when we talk a little bit more about counting principles, and we will see how the general principles will allow us to solve this counting monomials problem without using this recurrence, just by a more general procedure. But in the meantime you can sort of try and think about what these coefficients really are.